everyone. We're happy to have Noah Golowich presenting at our ASC seminar today. Noah is currently a second-year grad student in the theory group at MIT, where he is advised by Professor Kostas Daskalakis. His area of study focuses on theoretical machine learning, and today he'll be talking about sample-efficient, proper PAC learning with approximate differential privacy. And here's Noah.
Great, thanks, Kwankwan. So this is joint work with Badika Z, Ravi Kumar, and Pasu Manurangsi. So in this talk, I'm going to talk about privacy preserving PAC learning. And some of the motivation for this is that machine learning models nowadays are trained on sensitive data. And it's important to protect the privacy of the users who produce this data. So for instance, think about hospital data or personal health data. This is data which is, should be kept private. It's one way to do this is to study kind of certain formal models of privacy under which we can reason about the accuracy privacy trade-offs and prove theorems about them. So in this talk, I'm going to focus on the private PAC model, which was introduced over a decade ago. And there's been a lot of study on this line of work, in particular learning with approximate differential privacy. And an interesting recent development in this line of work is a connection that has emerged between private learnability and online learnability. So this was shown in a pair of papers by Alon, Livni, Maliaris, and Moran, and also by Bun, Livni, and Moran. And what these two papers showed is that private PAC learnability, and online learnability are equivalent in some sense. And in this talk, I'm going to discuss our recent paper, which answers two open questions by Bun, Livni, and Moran on the direction of this equivalence, which shows that online learnability implies private learnability. So feel free to interrupt me at any point, ask any questions throughout the talk. Okay, so I'll begin by giving some background on private PAC learning, and then I'll discuss our results and some implications of them. I'll begin by reviewing differential privacy. So in the model of differential privacy, we have a collection of individuals. Each individual produces an example, which in this talk will be a pair xi, yi, where xi belongs to some set x, which we think of as a space of features, and yi is a label, either -1 or 1. And a data set, Sn, is simply the set consisting of n examples. So n pairs xi, yi, for I equals 1 to n. And our goal is to come up with a randomized algorithm A, which is a private learning algorithm. In particular, it's going to take as input such a data set where the xi's can consist of, for instance, features for a bunch of patients in medical study, and the yi's will consist of labels indicating whether or not each patient has cancer. And this private learning algorithm will output a classifier, namely a function from x, the space of labels, which predicts, given any patient's features x, whether or not cancer is present in that patient. And the main requirement in this algorithm, from the perspective of privacy, is that this algorithm satisfies differential privacy. And here's the definition of differential privacy. We say that an algorithm A, which is a randomized algorithm, so it outputs a random classifier, is epsilon delta differentially private if the following holds. We want a certain property to hold for all pairs of neighboring data sets, Sn and Sn prime. And by neighboring data sets, I mean data sets which differ in a single example, xi, yi. So you basically take one user in the medical study and you replace them with some other user. And for any such pair of neighboring data sets, we want the following to hold. And this equation basically states that the distribution of A of Sn, the output of A in the data set Sn, is close to the distribution of the output of A on the data set Sn prime. So in particular, for all events E, we want the probability that E occurs under the data set Sn to be at most e to the epsilon times the probability that E occurs under the data set Sn prime plus delta. Now here, epsilon and delta are going to be certain parameters which indicate what degree of privacy your algorithm satisfies. In this talk, the specific values won't matter too much. You can think of epsilon as being a small constant, for instance, 1/100, and delta as being something that decays super polynomially with n. So for instance, you can think of delta as being n to the minus log n. For epsilon and delta, which are smaller, this inequality here becomes a stronger inequality, and therefore the privacy guarantee becomes stronger. So that's the definition of differential privacy. As always, feel free to stop me with any questions. And the second part of this, the model that we're going to be considering is the model of PAC learning. So what this model is basically making an assumption on the data, x1, y1 through xn, yn, that we're going to be feeding into our learning algorithm. So in particular, we're going to assume that we're given a known class big F of hypotheses. These are just binary classifiers, functions f from x to minus 1, 1. And second, we're going to assume there's some distribution P on the space x cross minus 1, 1, so that the data set Sn is drawn IID from this distribution, and we don't know P, so it's unknown. So each xi, y is drawn from P independently. And the goal in a PAC learning problem is to find an algorithm A, which again takes as input its data set Sn. And we want the algorithm A of Sn to output a hypothesis f hat from x to minus 1, 1, which minimizes the population error of f hat, denoted as error P of f hat, which is defined to be the probability for an example drawn, xy drawn from P, of the misclassification error, namely the probability that f hat of x is not equal to y, where xy is drawn from P. And in this talk, I'm going to focus on the realizable setting, which means that we're making the assumption on the distribution P, which is the following, that there exists some hypothesis f star, so that for all x, y in the support of the distribution P, f star of x is equal to y. So what this means is that the population error of f star is equal to 0. In other words, the class f is expressive enough to achieve population error 0. It turns out that in the setting of private PAC learning, this assumption is basically without loss of generality by recent work of Alon, Baimel, and Stemmer. They showed a reduction from the non-realizable setting to the realizable setting with really not a very large blowup in sample complexity. And finally, I'm going to find an algorithm A to be proper if the hypothesis f hat that it outputs belongs to the class big F with probability 1. An algorithm that's not proper is defined to be improper. Okay, so this is our model. Basically, we're aiming to minimize population error. And the private PAC model is basically the combination of the private and the PAC models. So in particular, we want an algorithm A, which solves the PAC problem that I mentioned on the previous slide. We want this algorithm A to be epsilon delta differentially private as a function of its data set Sn. So that's the goal. And as I mentioned in the first slide, there's a pair of recent works which characterize those hypothesis classes big F that have a private PAC learning algorithm achieving non-trivial error, namely error going to 0 as the number of samples n goes to infinity. And it characterizes these hypothesis classes as exactly those hypothesis classes whose Littlestone dimension is finite. Now, I'll next define Littlestone dimension. This is going to be kind of a central element of the talk. So to define Littlestone dimension, I need to introduce kind of a couple definitions about binary trees. So we're going to consider binary trees, such as the one shown on the left right here, which are complete and all of whose internal nodes are labeled by elements of the data space X. The labels of such a binary tree are going to be labeled by either -1 or 1. And basically, you can think of for each node, the edge coming out of the left is labeled by -1, and the edge coming out of it on the right is labeled by 1. And we say that this tree is shattered by a hypothesis class F if for each leaf L of the tree, there is some hypothesis FL, which labels each node on the root to leaf path corresponding to the leaf L according to the label on the edge coming out of each respective node. So this can be a little confusing. It's instructive to consider an example. So consider the green leaf in this tree here. What we want for this leaf, L, is that there exists some hypothesis FL. So the FL of x1 is equal to the label of this edge, namely -1. FL of x21 is equal to 1. And FL of x32 is equal to 1. And we want such a hypothesis FL to exist for each leaf. And there's going to be different hypotheses for each leaf. And so that's what it means for a tree to be shattered by the class F. And the Littlestone dimension of hypothesis class, denoted by LDIM of F, is simply the largest depth D. So there exists some tree which is shattered by F. So we're taking a maximum over all trees. And so you can think of tree which is shattered by F is basically kind of a measure of how expressive F is on the particular set of X's which label the nodes of that tree. Now, Littlestone dimension has been studied for a decent amount of time in machine learning theory. And in particular, it's a well-known result that the finiteness of the Littlestone dimension of a hypothesis class characterizes how many samples we need to learn it in the model of online learning. This is true in both the realizable and the agnostic settings of online learning. And that's why I said earlier that private PAC learnability is equivalent to online learnability. But for the purposes of our paper, we actually won't really make many explicit references to online learning. We'll kind of view Littlestone dimension as a combinatorial parameter that kind of allows us to manipulate a hypothesis class in certain ways. So you don't really need to know anything about online learning to understand anything in this talk. Okay, so I'll next give a few examples of hypothesis classes which have finite Littlestone dimension. The simplest example is any class F, which is finite. It is a finite number of elements, has Littlestone dimension bounded above by the logarithm of the size of the class. And this basically is just because in a binary tree, which is shattered by the class, the hypothesis for each leaf must be distinct. So the number of hypotheses in the class has to be at least 2 to the depth. And for many classes, this inequality is not tight, meaning the Littlestone dimension can be much smaller, the log of the size of the class. But one instructive example for which this bound is tight is the class of threshold functions. So suppose we have a domain X of size 2 to the D. I'm going to consider the class of threshold functions on this domain. There's 2 to the D such threshold functions. And they're labeled by 1, 2, 3, all the way up to 2 to the D. And they're defined basically exactly how you think they would be. Threshold I evaluates to 1 on some point J between 1 and 2 to the D, if and only if I is at most J. In this class, the threshold functions have Littlestone dimension D. And well, one way to see this is by looking at the binary search tree, basically for the domain of integers from 1 to 2 to the D. So here's an example for D equals 3. I'm showing a tree which has 7 internal nodes are labeled by the integers from 1 to 7. And this is shattered by the class of thresholds on the integers from 1 to 8. So, one example kind of showing how a leaf might have a hypothesis corresponding to it. This green leaf, for this green leaf, we want a hypothesis which evaluates to -1 on 4, that is to 1 on 2, and evaluates to 1 on 3. One example of such a hypothesis is the threshold which evaluates to 1 on some value X, if and only if X is at most 3. And you can check that there exists, a threshold in this manner for every leaf on the tree. And therefore, this tree is shattered by the class of threshold functions, and therefore, the Littlestone dimension is at least 3 for the case D equals 3. And you can generalize this for all D just by considering the binary search tree or the range query tree on the domain of size 2 to the D. Okay, so throughout this talk, I'll use D to denote Littlestone dimension. And next I'm gonna, actually, yeah, so one more background slide. I'll next compare the prior work on sample complexity of learnability in both the private and non-private settings. So in the setting of non-private PAC learning, the minimum number of samples n needed to achieve error, which goes to 0, is bounded both above and below by constant times the VC dimension of f. VC dimension is another combinatorial parameter introduced by Vacnik and Sherveninkis in 1971. I won't really mention this talk, but suffice to say that there is a combinatorial parameter which characterizes learnability in the non-private PAC setting. In the private PAC setting, I mentioned that Littlestone dimension gives such a characterization. And I'm showing here the quantitative bounds. So on the upper bound side, Bun-Livni-Moran showed that the number of samples needed to achieve non-trivial error grows as constant roughly to the Littlestone dimension of the class F. And in terms of lower bounds, along Livni, Malderas, and Moran showed that the number of samples n has to be at least the iterated logarithm of the Littlestone dimension of the hypothesis class. So this is the number of times you have to take log in order to get down to 1. In general, this is going to be kind of a very, very small parameter. It does go to infinity as Littlestone dimension goes to infinity, but it's kind of as small as you can get, not in a formal way, without being constant. And so this gap between upper and lower bounds here is really, really large. But it is a finite gap, and that's why there's an equivalence. So a couple of remarks on these two kind of private and non-private PAC settings. First of all, VC dimension is always bounded above by Littlestone dimension. And this reflects how non-private PAC learning is always going to be easier than private PAC learning. And the gap between VC dimension and Littlestone dimension can also be arbitrarily large. So for instance, for the class of thresholds, which I mentioned on the previous slide, the VC dimension is 1. The Littlestone dimension is logarithm of the size of the domain, which can be arbitrarily large. The second remark pertains to this upper bound, the number of samples n in the setting of private PAC learning. And if we want to decrease the gap between upper and lower bounds, we might say, okay, let's try to improve the upper bound. Unfortunately, we can't actually hope for a bound which is sublinear in Littlestone dimension if you want this upper bound to depend only on Littlestone dimension and not any other parameters of the class. This is because there are hypothesis classes F whose VC dimension is equal to Littlestone dimension. And we know that VC dimension characterizes learnability in the non-private setting. So we can't hope to get a upper bound which is better than VC dimension in any, for any class F. And therefore, for such classes F, we can't get something that's sublinear in Littlestone dimension. I'll mention this later, but there is hope of potentially kind of avoiding this obstacle by, conjecturing bounds which depend on both VC dimension and Littlestone dimension in particular ways. Okay, so now I'll talk about our results. Feel free to let me know if you have any questions now. Okay, so just to kind of fix the notation, we're considering hypothesis class F of Littlestone dimension D. That's a class of binary hypotheses. And we're going to let P be a realizable distribution on the space X cross minus 1, 1. And here's our main theorem. For a number of samples n, which roughly grows as d to the 6th over epsilon alpha squared, there is an algorithm A, which takes as input n IID samples from the distribution P. This algorithm is epsilon delta differentially private, and it outputs with high probability a hypothesis F hat in the class big F, which has classification error at most alpha with respect to the distribution P. Note that the parameter delta doesn't explicitly show up in the sample complexity bound. That's because it's the dependence on delta is, polylog 1 over delta, so I'm hiding it in the old tilde notation. So we call it the fact that this hypothesis output by the learner belongs to the class big F means that our algorithm is a proper learning algorithm. And as I mentioned before, the previous best known bound was exponential in the Littlestone dimension. And also that learner was not proper. So we improve both kind of qualitatively and quantitatively on these prior bounds. Okay, so over the next few slides, I'm going to discuss the proof of this theorem. I'll begin by giving an overview of the proof. So the first step is to show the existence of an improper learner, which is differentially private and has polynomial sample complexity. And this improper learner satisfies an additional special property, which is that the classifier or hypothesis that it outputs is actually a special type of hypothesis known as an SOA classifier, which corresponds to some subclass of the base class, which in turn satisfies a special property that we're going to call K irreducibility. I'll define what that is in a moment, and also define what SOA classifier is in a moment. But just kind of from a high level point, we're going to then use this property of irreducibility of that SOA classifier together with a min-max swap, namely applying Sines min-max theorem, in order to upgrade this improper learner to a proper one. Now, the notion of irreducibility is kind of essential in both steps 1 and 2 of the proof, namely both getting an improper learner with polynomial sample complexity and then making it proper. So I'll now define kind of what irreducibility means. In general, we have this notion of K irreducibility for general positive integers K. In this talk, I'm going to really focus on the case K equals 1 because that gives sufficient intuition to reason about things. And so here's the definition of one irreducibility. We say that a hypothesis class G, consisting of binary hypotheses F on the space X, is one irreducible if for any hypothesis X, there is some bit B either -1 or 1, so that the following equality holds. That the Littlestone dimension of the set of hypotheses in G, which evaluate to B on the point X, is equal to the Littlestone dimension of G. In other words, restricting the class G to only those hypotheses which take the value B on X does not decrease the class's Littlestone dimension. Now, why is this notion of irreducibility important or useful for us? Well, it turns out that the SOA classifier for classes which are irreducible has a certain stability type property, which is conducive to the SOA classifier being private. And there's been kind of a fair bit of work in recent years that show stability defined in a loosely defined sense is useful in terms of developing private learning algorithms. And so, this is kind of can be viewed as, another kind of, point in the direction. Basically, irreducibility leads to some sort of stability. Okay, so for the rest of the next few slides, I'm going to really focus on the first part of this proof. The second part where we use this min-max swap is kind of a standard technique, and I think most of the kind of novelty in our paper is really in the first part. So I'll work towards kind of showing you what the stability property is. Before I do so, however, I'm going to define SOA hypotheses and give an example. So I'll first fix a bit of notation. For a subclass G of the base class F and a bit B and a point X, I'm going to define G restricted to XB as a set of hypotheses G, which take the value B on X. So this is exactly what shows up kind of in this definition of irreducibility here. And we refer to this as the restriction of G to XB. Now, for such a class G, the SOA hypothesis for G, denoted by SOA G, is defined as follows. For any point X, we define SOA G of X to be 1 if the Littlestone dimension of G restricted to X1 is at least the Littlestone dimension of G restricted to X minus 1. And SOA G of X is -1 otherwise. So we're always setting SOA G of X to equal to a label either 1 or -1, which maximizes the Littlestone dimension of G restricted to X and that label. one way to think of this intuitively is we're setting SOA g of x to whichever label kind of keeps the class larger when its size is measured by Littlestone dimension. And the motivation for this, for the SOA hypothesis, comes from the setting of online learning, when we receive examples X in an online manner. And often we want to predict a label which is equal to SOA g of x, because we're kind of predicting the label which is most consistent with a certain class of hypotheses. And for those of you who are familiar, this is related to something like the halving algorithm. Okay, so here's an example for the class of point functions. Let's consider the space X consisting of 5 points x1 through x5, and the space of hypotheses G, which consists of G1 to G5. And these are just the point functions in the points x1 to x5. So in particular, G1 evaluates to 1 of the point x1 and -1 elsewhere. G2 evaluates to 1 of the point x2 and -1 elsewhere, and so on. So if you consider the kind of the matrix showing Gi of xj, this is just the identity matrix with the zeros replaced by -1s. And okay, a couple remarks about this class. I've copied the definition of reducibility here. And I'll note that the class G here of point functions is irreducible. Its Littlestone dimension is equal to 1. That's because it shatters basically any point, and you can check that it does not shatter any tree of depth 2. And moreover, for any point x, the Littlestone dimension of the restriction of G to x minus 1 is equal to 1. So why is this the case? Well, let's focus on x1, for instance. When we restrict the class G to the set of hypotheses which take the value -1 on x1, we get G2 through G5. And the set of such hypotheses, shatters, for instance, x2, or x3, or x4, or x5. So it must have Littlestone dimension 1. So this shows that G is irreducible. But we also note that for any point x, the Littlestone dimension of G restricted to x1 is equal to 0, because that consists of the single function which takes the value 1 on x. And any class consisting of a single function is Littlestone dimension 0. So what this means is that basically by our definition of SOA, the SOA hypothesis for each point x is equal to -1. Where the class G is the class of point functions. And this shows one interesting thing, which is that the SOA hypothesis need not belong in the class. There's no point function which is -1 everywhere, at least the way I defined it. Okay, so now that I've defined SOA hypotheses, I can now kind of talk about the stability result I mentioned a few moments ago. So I'll begin by just kind of rephrasing the definition of irreducibility. In particular, for class H, which is irreducible, one irreducible, for any point x and for any bit b, we have that b is equal to the SOA H of x if and only if the Littlestone dimension of H restricted to xb is equal to the Littlestone dimension of all of H. So we're basically saying that SOA chooses the bit b, which does not decrease the Littlestone dimension of H restricted to xb, for each point x. And here's the main stability lemma. It says the following. Suppose we have two classes, H and G, and H is a subset of G. Suppose also that their Littlestone dimensions are equal, and that H is one irreducible. Then the SOA hypotheses for H and G are identically equal. In other words, for all points x in our space, SOA G of x is equal to SOA H of x. And to prove this lemma is really kind of very simple. It's 2 lines, so I'm going to kind of present it in this fully here. So let's fix any point x, and suppose for simplicity that SOA H of x is equal to 1. The case where it's -1 is handled kind of symmetrically, so I won't cover that. Then we have the following train of inequalities and equalities. First of all, the Littlestone dimension of G restricted to X1 is at least the Littlestone dimension of H restricted to X1, because H is a subset of G and the restrictions are also subsets of each other. Next, we're kind of going to be using irreducibility, showing that the Littlestone dimension of H restricted to X1 is equal to the Littlestone dimension of H. Oops. This uses lemma 1, basically because we assume the SOA H of X is equal to 1. And finally, Littlestone dimensions of H and G are equal by assumption. But when we look at the entire chain of inequalities we've shown, what we have is the Littlestone dimension of G restricted to X1 is at least Littlestone dimension of G. But G restricted to X1 is also a subclass of G. So we also have an inequality in the opposite direction. So these two Littlestone dimensions are equal. And it's easy to see in such a case, the Littlestone dimension of G restricted to X minus 1 must be less than the Littlestone dimension of G. If it were also equal to LDIM of G, we'd be able to construct a tree of depth D plus 1, which is shattered by the class G, which would contradict the definition of Littlestone dimension. So what this means is that the SOA G of X is equal to 1. And as we assumed, 1 is equal to SOA H of X, so that basically that kind of concludes the proof. So this proof is kind of extremely simple, and the lemma is very simple. But essentially, what this lemma allows us to do is it allows us to kind of abstract out exactly kind of the right definitions, namely of irreducibility, and also the right conditions, namely that we have H, which is a subset of G, and those two dimensions are equal, which in turn allow us to show that two SOA hypotheses are everywhere equal. And this property of SOA hypotheses being equal is going to be a major factor in the lemma I'm going to show next, which is kind of the main technical lemma to prove our upper bound on the sample complexity of private learning. Okay, so here's just a review of, I just copied the definition of SOA hypotheses. One kind of aside I'm going to note before stating our main lemma is that for an irreducible class G, we never have to break ties in the definition of SOA hypotheses. We never have Littlestone dimension of G restricted to X1 is equal to that for G restricted to X minus 1. This is just because if they were equal, they'd both be equal to Littlestone dimension of G. And this would basically, as I said in the previous slide, lead to a tree of depth larger than G's Littlestone dimension, which is shattered by G. And intuitively, it's kind of nice that we don't have to break ties, because how would we break ties? In practice, we kind of have to do it based on some property of the data set, potentially. And doing so could ultimately lead to some kind of privacy loss, because certain private data could somehow leak into how we break those ties. So that's just an aside, it won't really matter. But here's the main step in our proof. It's this lemma, which I'll refer to informally as relaxed global stability. And here's what the lemma states. For any realizable distribution P, there is a hypothesis sigma star, binary hypothesis from X to minus 1, 1, so that given a data set Sn consisting of n examples, which is drawn IID from P, and where n is a polynomial in the Littlestone dimension G in D, we can construct from the data set Sn subclasses of F, namely G hat, and I'm going to call these subclasses G hat 1 through G hat J. And these subclasses satisfy the following two properties. First of all, the SOA hypothesis for each subclass, namely SOA G hat J, has low population error with high probability. And second, with a reasonable probability, roughly say 1 over D, over the draw of this data set, there exists some class G hat J so that its SOA hypothesis is identically equal to sigma star. So At a high level, kind of this second point in the lemma is the more important. It's kind of the crux of the argument. Basically, what we're showing is that some SOA hypothesis for a class that we can construct solely off of the data, namely the data set Sn, is equal to a hypothesis sigma star, which depends only on the distribution. So somehow, if we had like an oracle that could just tell us sigma star, then we'd basically be done, because we could just output sigma star as the output of our private learning algorithm. And sigma star does not depend on the data at all, so it would be trivially be private. We don't have such an oracle, but the second property here kind of allows us to, in a sense, simulate such an oracle. And that's what I'll discuss on the next slide. So in particular, the way we use this lemma of relaxed global stability is as following. We're going to take a number of draws of independent draws of such a data set Sn. Basically, you can imagine taking our full data set and splitting it up into some number m of blocks Sn1, Sn2, and so on. And the number of independent draws of this data set Sn is going to be roughly something larger, a little bit larger than D. And what this lemma tells us is that if we make more than D draws of data set Sn, we're going to see some sigma star appear in the SOA of G hat J many times with high probability, because we're making, for any one draw, it appears probably 1 over D. So with more than D draws, we see it a lot. And so what our goal is we just want to kind of find a way to somehow privately select such a sigma star in a way that is differentially private. And it turns out that there's been a bunch of techniques in the differential privacy literature which allows us to exactly do this. So what we do is we apply a private sparse selection protocol by Ghazi Kumar Monarangsi, which basically kind of completes the proof of our main upper bound. In particular, what they show is that assuming that such a sigma star appears multiple times, which it does, and there's a way to kind of choose such a sigma star, which is epsilon delta differentially private, and by this lemma relaxed global stability, that sigma star will have low population error. Okay, so that's kind of the overview of how this lemma implies our main theorem. I'll next discuss a little bit more the proof of this lemma. Okay, so I've copied the lemma kind of at the top of this slide, and in order to give the proof of this, I'm going to introduce a little bit more notation. So for a distribution Q and a positive real number alpha, which represents an error threshold, I'm going to set FQ alpha to be the set of hypotheses F, whose population error under Q is at most alpha. So you can think of this as kind of the set of hypotheses, which is good enough for our purposes. And I won't specify exactly what alpha is, but think of it as just kind of an acceptable kind of error cutoff, which the user who just basically can be an arbitrary kind of threshold. And the idea behind the proof of the relaxed global stability lemma is the condition on whether or not this assumption, which I'll explain in a moment, holds. And this assumption depends on this parameter alpha, as well as some other parameter alpha delta. And this assumption states that the following. Let's consider a given sample Sn. We want two things to hold. First of all, the littlest dimension of the set of hypotheses in F with empirical error at most alpha is equal to the set of hypotheses, is equal to the littlest dimension of the set of hypotheses in F with empirical error at most alpha minus alpha delta. So the empirical measure Pn hat is simply the uniform distribution on the space of examples x1, y1 through xn, yn. And what the first part of this assumption is saying is that when we decrease alpha from alpha to alpha minus delta, the Littlestone dimension of the space of hypotheses, which has empirical error either at most alpha or alpha minus delta, Littlestone dimension will not decrease. And the second part of this assumption states that the class of hypotheses with empirical error at most alpha minus alpha delta is one irreducible. So at first glance, it may seem arbitrary that we're making this assumption. Hopefully, I'll be able to give you a sense of why this, how this folds into the rest of the proof. So let's first consider what happens if this assumption holds. Well, at this point, we can actually use a result from proven by Vapnik and Chovanenkis, namely that of uniform convergence. So in particular, by this theory, by VC theory, we have the following inclusion of hypothesis classes. First of all, the set of hypotheses with empirical error at most alpha minus alpha delta is included in the set of hypotheses with population error at most alpha minus alpha delta over 2, which in turn is included in the set of hypotheses with empirical error at most alpha. And the reason these inclusions hold is we're just using uniform convergence with error parameter alpha delta over 2. And uniform convergence implies in this case, because VC dimension is always bounded above by Littlestone dimension. Now, once we have this chain of inequalities, well, the first part of this assumption, which is that the green and the brown classes have equal Littlestone dimension, implies that all three of these classes have equal Littlestone dimension because the second is sandwiched between the first and third. And second, using the second part of this assumption, namely irreducibility, together with the stability lemma on the previous slide, we get that the SOA hypotheses for the brown class and the class shown in black are equal. So in particular, that lemma showed that if you have two classes that are containing, one is contained in the other, that have equal Littlestone dimension, and we have irreducibility of the first, then the SOA hypotheses are equal. And that's just exactly what we're using here. But this is a really nice property because we have that a class shown in brown, which depends only on the data, has an SOA hypothesis, which is equal to that of some class, which depends only on the distribution P, not on the data at all. And this is really exactly what we want to show for this lemma of relaxed global stability, namely that something that's empirical based is equal to something that's based on the population distribution. So in particular, if this assumption holds, we can just set sigma star to be equal to this class shown in black, and we'd be all set. Of course, the challenge comes in when if this assumption doesn't hold. But there's actually one thing that really makes it possible for us to deal with this case. And I'm going to focus on the case when the assumption doesn't hold due to this irreducibility failing. The case when it doesn't hold due to these Littlestone dimensions being unequal is actually even a little bit easier. So if this class is not one irreducible, then by the definition of irreducibility, we can find some point x such that the Littlestone dimension of the restriction of this class shown in brown to both x1 and x minus 1 is strictly smaller than the Littlestone dimension of the class shown in brown. That's just the definition of irreducibility. And at this point, what we've done is we've decreased Littlestone dimension by 1. And we assume Littlestone dimension is finite, and it has to be an integer. So we can only decrease, a finite number of times, in particular d times, where d is Littlestone dimension. And so what we're going to do now is we're basically going to recurse on two classes, namely the restriction of f to x1 and the restriction of f to x minus 1. And we're just going to repeat this entire process with these two classes. And well, there are some technical difficulties in this. It's not, it's quite a bit, more involved than the argument for this, top level recursion case that I've presented in this slide. But it turns out that by using k irreducibility, which is a generalization of one irreducibility, we can actually make this whole recursion work in a way that allows us to define a sigma star that satisfies the properties of this lemma. Okay, so that's kind of the idea of the proof. In the last few minutes of the talk, I'm going to discuss some implications of our main result. And in particular, what our main result does, it allows us to give a characterization of when private query release, otherwise known as sanitization, is possible for binary hypothesis classes. So the problem of sanitization is the following. We want to give an estimate for the mean of each binary hypothesis over a given data set S. We're no longer making any distributional assumption of S such that it's drawn from some distribution. This can be an arbitrary data set S. So for instance, if S consists of kind of attributes of patients in a medical study, such as the ones shown here, a sanitizer might output in a private way certain statistics, such as the fact that 2/3 of the data set is a smoker, 1/3 of the data set is a smoker with cancer, and so on. So here the Fs represent kind of the attribute of being a smoker, the attribute of being a smoker and having cancer, and so on. And here's the definition of a sanitizer. For given X and F, an algorithm A is a sanitizer for the class F with accuracy alpha and sample complexity n if the algorithm is epsilon delta differentially private. And second, for all data sets S, consisting of n points X, the output of A on S is a function est, which maps from F to the reals -1, 1. And this has to satisfy with high probability over the algorithm's randomness. We have uniformly over all hypotheses F that est of F is a good approximation of the mean of F on the data set, where this approximation is an additive approximation up to error alpha. Okay, so intuitively, you should think of standardization as something that's stronger than learnability. In learnability, we want to find a single hypothesis, which is, has good error in terms of a certain distribution. For sanitization, we actually want to compute this estimator, which has a certain property that holds over all hypotheses. So you might think that this is kind of a much harder problem than learnability, but a quite remarkable result by Bousquet, Livni, and Ron showed that actually private proper learnability implies the existence of a sanitizer. So if you kind of ignore quantitative bounds for the moment, this means sanitizing is actually somewhat surprisingly no harder than simply the problem of privately learning with a proper learning algorithm. And now recall that what I showed early in this talk is that finiteness of Littlestone dimension implies that you have a proper private learning algorithm for that class. And so basically you can just kind of glue these two results together and get that finiteness of Littlestone dimension implies that you have a sanitizer. And what we actually show is that there's a quantitative version of this result, which is the following. Suppose you have a class F with Littlestone dimension D and dual Littlestone dimension D star. Then for a number of samples n, which is polynomial in both D and D star, this class F has a sanitizer with sample complexity n and accuracy alpha, where the number of samples grows polynomially in 1 over alpha and also 1 over the privacy parameter epsilon. Now, I haven't defined what dual Littlestone dimension is. Simply stated, it's simply the Littlestone dimension of the dual class of F. That's not too important. Really, kind of the main property of it that is interesting is that D star is bounded above by a double exponential in the Littlestone dimension D. And what this does is this immediately shows that classes with finite Littlestone dimension are sanitizable, mainly have sanitizers with polynomial sample complexity in 1 over alpha. But the converse direction was also shown several years ago by Bunn, Nassim, Stemmer, and Vadan. And so what this means is that binary hypothesis classes are sanitizable if and only if they have finite Littlestone dimension. And that's kind of the main corollary of our results. Okay, so that's basically it. I'll conclude by mentioning some open questions. The main kind of remaining open question is to characterize the sample complexity of learning with approximate differential privacy. Ideally, we'd be able to find a combinatorial characterization that does this up to a constant factor. So for instance, the VC dimension does so for the problem of non-private PAC learning, as shown by Vapnik and Shevardinkas. Littlestone dimension does so for the problem of online learning. And one-way public coin communication complexity does so for the problem of PAC learning with pure differential privacy. Unfortunately, approximate differential privacy is a harder question, but there's some intermediate questions which might be kind of useful in terms of moving towards solving this question. So one kind of immediate question is, can you improve our bound which scales the Littlestone dimension to the 6th to something that's linear Littlestone dimension? As I mentioned before, you can't get something that's sublinear if you only want your bound to depend on Littlestone dimension. But you could hope for more refined bounds as well. So the best known lower bound of the sample complexity of private learning is something that's in the order of VC dimension plus log star of Littlestone dimension. Can we get something that's polynomial as an upper bound, polynomial in VC dimension and log star of Littlestone dimension? This would be much, much stronger than our result, but maybe it's possible. And finally, can the sample complexity of proper private learning with approximate differential privacy be much larger than that for improper private learning? In other words, is there a gap between proper and improper? There is such a gap for pure differential privacy, but we don't know it for approximate. So that's it. Thank you for listening, and I'm happy to take any questions.
Thanks, Noah. Are there any questions?
So Noah,
yep.
I was just wondering, what's your guess onto like what the right upper bound should be?
So I think it's either polynomial in VC or log star of Littlestone. I think that's somewhat likely. I think there's also a decent chance that there's entirely different combinatorial parameter that might characterize it that we just haven't thought of yet. So that could lie somewhere in between this thing and our upper bound. But I've thought a little bit about improving this lower bound, and that seems pretty hard. And I don't know, improving the upper bound is more tractable, maybe. Yeah.
I see. I mean, it seems a little strange that it would be like log star is the right quantity there, right? Or maybe you think that's inherent.
Yeah, I mean, I'm not sure. Like, basically, this log star comes about on the simple class of learning thresholds, and so we don't really have any examples of hypothesis classes which are provably harder than thresholds to learn. So I guess kind of what this boils down to is like, are thresholds kind of the hardest possible? They complete in some sense for private learnability, and maybe they are. That seems possible.
That makes sense.
So I have a question. I'm just curious, where in your argument so I can kind of see where in your argument the delta comes from, like because you say with high probability we get this thing which only depends on the true model and not on the data. I'm just curious about where the kind of epsilon comes from. Is it from how you knit together the cases of the recursion?
So the epsilon and delta, kind of the only part where we're kind of explicitly dealing with those is in this sparse selection protocol.
Mm-hmm.
So basically the place the epsilon comes from in this sort of argument is really due to a privacy preserving algorithm known as the exponential mechanism, mm-hmm. which was introduced by a while ago. Yeah, well, and basically, are you familiar with that, or?
Yeah, so presumably it's the same thing from database DP.
Yeah. So we're basically kind of sampling from the Gibbs distribution, and the kind of temperature parameter is epsilon.
Right.
And the
Does that mean we're not going to hit exactly sigma star? In fact, I mean, because presumably if you're saying we select actually sigma star with high probability, then apart from delta of the time, we're hitting something which is actually independent of the data.
So we're not going to select sigma star with probability 1.
Right.
You know, that actually wouldn't contradict privacy if we did that, because sigma star doesn't depend on the data at all. But you know, that's just not something that we can get. What our private algorithm will do is, you know, it won't necessarily output, you know, any one given sigma star with high probability, but it's possible there's a bunch of different sigma stars, and it'll kind of choose between them in kind of a smooth enough way that preserves privacy, and that's what it'll be outputting.
Thanks.